Hello, Angela.
Hi,
Hey, how are you?
I'm good. How's everybody else? Oh, something changed. What happened?
We have Avinash here. Oh, what did you say?
We're not in the same classroom anymore?
Oh, yeah, we're not in the same classroom because I'm supposed to stay home, right?
Oh, okay, okay, cool, cool.
I can go to the department, but then I thought this is convenient. Yeah, so this is, I'm at home. Yeah,
Okay, cool.
I think we might just be able to do, okay. Let's see. So we have two votes. Let's see. So let's hope this thing works well. How is the isolation going? Is it bearable?
I'm talking to the lamps in my room, so not very well.
No. not good. But the end is not very near, right? We don't see anything. Not surely in a week or so. What April 7th is the date, correct?
For end of isolation?
Or
Well,
stay
yeah,
home,
and
right?
that's probably just a preliminary, you know.
Yeah, it doesn't look like it's going to go away by then.
Hey, Moses. Oh,
Hey,
so I don't see Moses now. Okay, so maybe I have to do great. Better. Oh, so we have one more. So is it John?
yeah,
Brittany can conduct this. Wife, probably. Jordan, are you there?
he was just there.
I was there. Okay, I was not seeing the whole
Video.
grid. I was seeing only Angela.
Are you at home then? Or where are
Yes,
you?
I'm at home. So at least yesterday it seemed to work well. So we will see. This works with the stay in order, right?
Yeah,
But I did ask for, I mean, they had some rules that if you're coming to the department, you should let us know. So I did inform them that I might be using the
mm-hmm,
so that they don't drive me off.
mm-hmm.
And if you're in other countries, they start beating you up. I saw some videos where if you go out, you get beaten up.
Well, in North Korea, they're shooting, so I think it's better off.
Okay, it was. Okay.
They're literally shooting people who have the virus. Oh boy.
So we will have two boards. Why do I have two boards? Because my computer audio doesn't work. So the other one is for audio and video, and one is for seeing you guys through, and the camera is connected to this. So hopefully everything works. I did press the recording because yesterday I had two classes. For both classes, I messed up with the recording, and the board did not get recorded. The audio did get recorded, but the board did not get recorded. So hopefully I don't mess up today. And where's Jordan? He wakes up. There you go. Are you in the bathroom, Jordan? You just woke up and just show your hand. Hey, I cannot hear you. Jordan.
He has muted. Okay.
What did you say?
No, you just showed your hand, so I thought you could pick the camera and you to the bathroom.
I had to go get this thing of candy.
So now you're at home, you can have all your candies and it's not bad. So remember, we're going to be recording this, but what I have found is that I just have to post this privately. That's one option. The video of this lecture. So that's what I'm doing in other classrooms. So I just don't post it publicly. But then the hassle with that is that I have to give the email of all the participants who want to see it so that they can log in into YouTube and see it. So it's up to you guys. If you guys I can make it public, and then it's very easy to view. But you guys really did send me the email, so I assume that you guys are fine with that.
Yep.
Yeah.
Okay, cool. Okay. We did. So we have we do the homework. Oh, there is a homework due today, right?
Yes.
Is it okay? Is it possible that you guys can submit it? Or Moses is really having an expression.
I was going to ask you about that. I've been a very poor manager of my time, and we have an exam on Thursday in quantum. I was wondering if I could turn it into you on Friday.
Sure. That's that should be fine, I think.
Okay. Thank you.
That I have others. I think others should agree first, actually, because
Yeah.
I have no text. So is that fine?
Yeah,
Homework is on to Friday. But the only thing is that I keep posting the new homeworks. Okay, this is the detailed current homework, but I post the new homework and it piles on for you guys. So we have. Is this visible? Oh, by the way, is this readable? Let me. You guys tell me. Homework 6. Is this readable? Or should I zoom in? I can't zoom in. No, no one's good. Okay, so how about this?
I think I just need to make your full screen. I'm trying to remember how to.
So one of the boards should have this. Correct? Zoomed in. Oops. Still no?
Yeah, it's readable. There's just a little bit of a glare from the light.
From the light, I think. So I couldn't see.
Yeah, but
It's
it's
just that
not
top
that.
thing.
It's really only in like 2 spots. It's not. I don't know that would be a problem.
Oh, okay.
I'm looking into the second video, the zoomed up video. I think that is pretty good. I don't know which camera that is yours.
So
Oh,
write it here.
yeah, that's. Yeah, the zoomed up. Yeah.
The zoomed in camera is pretty good.
Yeah.
So there are 2 of the boards, so you should be able to.
Oh, okay.
Okay. So keep switching from one to the other. The recording will have the center one, but then that will be a local recording. I think it's better. We'll see how it goes. Okay. So homework 6. Oh, when is this? You know. So no, it's due today, right? So, but flexible. I haven't posted the 7, but it's almost ready for probably by afternoon or evening. You should have this up, and I'll make this due 31st. Let's say Tuesday, next Tuesday. And apparently we had scheduled midterm 2 for Tuesday, next Tuesday. Are we ready for that?
I don't think so.
To be honest, no. But to be honest, no. Is it possible? I suppose.
I was thinking because we lost 1 week in between and we just started, right? I mean, so we had a break of 2 weeks. Even I have to recall what we were doing. So how about postponing it by 31st, right? So 1 week or 2 weeks.
Next Tuesday?
Next, I was even thinking 2 weeks. What do you guys say? It's just that it's going to get closer to the final exam, but we don't even know whether we're gonna, how the final exam is going to work. It seems like we just started the call. That was my perception, but it's up to you guys. Will you? Okay, here's the question for you guys that you can choose from. Would you like the exam to be on April 7th or April 14th? Or probably April 6th or April?
Either one that far away is okay. I think just like coming back from all this and like, especially for me, like I've been I had to still work my other job, and so trying to figure out all this stuff with D2L and making sure you get the recordings, and I feel like I'm a little behind, to be perfectly honest, just a little bit. The extra week thrown in, that put us like 2 weeks out from the last time we sat in a classroom. I feel like I'm a little out, so test next week feels a little early, but I guess it's possible. Especially because we have a quantum exam this Thursday. So
you guys have a quantum exam this Thursday? Wow.
Yeah, so this week my focus is pretty much just going to be quantum.
So it is still going on, right? Exam?
What's that?
The exam is still scheduled for Thursday. Did you make sure of that? That's even that might get postponed.
It is, yeah.
Yeah, I think we haven't actually had an exam in quantum yet, so I think
Right.
he's trying to get it in because we were trying to get an exam was it supposed to be last week when we returned from spring break?
No, actually, it was scheduled. We did talk about having it this week,
Okay.
but yeah, it's confirmed for Thursday.
Okay.
And
So
he's
how about this? I think
just giving us a day to do it, so like I work
How about that?
Thursday evening I would do it, so
Well, what he sent in the email actually was that he was going to give us from like 9 a.m. to 5 p.m. to do it.
No, he changed that
Oh,
to
he
a
changed
whole
that?
day.
Okay.
Yeah.
Okay.
It's like an open book sort of thing. I mean, open exam, I guess. I mean, you give the questions and then the next day it's due.
Oh, okay.
Yeah, he changed it because I emailed him and said, I'll be working until noon, and then from noon until 3:45 I have office hours, and if I get
Gotcha.
I won't actually have any time to actually work on the exam. So he said, yeah, it makes sense. People probably have stuff to do during the day or responsibilities. So he opened it up basically to turn in the next day because I won't get to work on it until really probably about 5. And I'll work from 5 till whenever I finish.
Yeah. Okay. Cool.
Whatever you want.
About this exam, shall we have it 2 weeks down? So
Yeah, that's fine.
Yeah, that's fine.
Let's get used to this whole thing. Like it is new for me too. I mean, so let's see, April 13th. I think April 13th is the Tuesday. And just to write it down, we have a final exam too, right? Assuming we all survive. So, Friday. I cannot write in class at this point. Oh yeah, that was one thing. I always wanted to have an oral exam in my students. What do you guys think of oral exam?
How would that work? I mean, not problems, but only conceptual questions? Like,
Now I'll make you guys work on the board. Something like that.
on the board?
Oh, you guys may not have a board, right? Or maybe
Yeah. I don't.
Okay, now we will have a take-home exam. That's easy. Yeah, so like
That's what
without a board is hard.
I talked to. That's what all the professors are pretty much doing. Just take home.
Yeah, I think that's it.
Kind of hard to do anything else.
Yeah, that's the way to assess, I suppose. Okay. So let me move the board to 1. Oh, does it move? No, come on. Okay. Today we want to talk about what are all Lagrange multipliers. And instead of really going by the defining the whole thing, I will actually try to do it using an example. And remember, I had pointed out earlier that Lagrangian cannot really pick up quantities like the normal force and the force of tension. You never see force of tension, force of normal force when you're doing Lagrangian mechanics. And why is that? And can we do something so that we can get the input from that also? So before we go ahead, so maybe just for discussion, so how would you explain the normal force to someone? Let's say in your class, you guys all teach.
It's acting perpendicular to the whatever other forces, if it's gravity or
Surface. The force that acts perpendicular to the surface.
Yeah, and why? That's correct. And why do you need the normal force? Or is that?
it is third law, right? Action reaction law.
Oh, no, yeah, maybe, but I'm saying some more. Yeah, keep saying. That's all correct statements. So maybe one can state it as if you have a surface and
Objects from passing through another object, I guess.
tell it. I couldn't get you, Jordan.
It's the force that you need to talk about objects. Otherwise, objects would just like pass through stuff. You know,
Yeah, exactly. That's what I was trying to come to. So when we have a floor, especially, the idea is that we are all supposed to be standing on the floor, right? We are confined on a surface in a sense, right? Or confined on the surface of Earth. And to capture that in Newton's law, you say that the normal force has to be there. Otherwise, as Jordan said, yeah, we'll go through the surface of the Earth because gravity is only force acting. Gravity should act, make something accelerate, but it doesn't accelerate. So to compensate that, you have a normal force. So in a sense, in that way of saying it, you can say that the normal force is a constraint, or to begin with, you have a constraint that some object is confined on a surface, and the normal force is taking care of that force. So the Lagrange multiplier is going to deal with constraints. Right. So we'll talk about at least in specific example what constraint means. So let's so the example we will do is simple pendulum. And the simple pendulum is, as we have done this a different number of times. This has been our reference example sort of again and again. And that's your angle, let's say angle phi. Angle phi, and that's increasing counterclockwise. And for let's say this is phi hat. That's your hat. Unit vectors, and that's also because this is actually going. It's going to swing around. So to begin with, let's say when we write a Lagrangian, this parameter, this angle phi, is the only thing that shows up, right? If you remember the Lagrangian for a pendulum, the differential equation is all in terms of angle phi. You can of course write it in terms of x or y and so on, but it's easiest is in terms of phi. So I talked about a constraint here, So what would you say is the constraint for a simple pendulum? By a simple pendulum, I'm saying it is moving in a plane. So it's already moving in a plane, so that's a constraint, right? In general, a simple pendulum doesn't have to be moving in a plane. Is that clear?
Yeah.
Right. Does it move in a plane? We discussed this before.
The
Does a simple pendulum move in a plane?
Not perfectly.
Not perfectly.
And it could, I mean, it could even move
It
in
has to be constrained to
2 dimensions, yeah.
That again? No, I didn't get that, Jordan.
I said it does if you constrain it to the plane. Yeah, it does move in the plane.
So if you're on the North Pole, it will move in a plane, correct?
Mhm.
Or if the initial conditions are such that you direct your velocity towards the center of the, or along the diameter of the Earth, then it will move in a plane. In general, it's a spherical pendulum. That's the idea of so-called pendulum. But let's say that our initial conditions are such that the pendulum is moving in a plane. That's surely a constraint, but after that, is there any other constraint?
Yeah, because you mentioned tension being something like, so tension constraint.
Very, very good. So tension is going to be so, but what is the actual constraint? Tension is going to be the force that will make it go in a constraint. But what is the constraint itself?
Length of pendulum.
Length of a pendulum has to be fixed, correct? So, but that's good, but more, make it more specific. Yeah, that's correct. That's what I was looking for, but make it more specific.
The mass is confined to move in a circular.
That's correct. It has to move in a circle, right? So because the length L of the string, or let's say it's a rod, if it's a string beyond certain angle, it might just collapse, right? It may not keep the tension in it. So there is a constraint here. So the constraint would be that x squared plus y squared is equal to L squared. That's what we are looking for. And I'm going to, so the idea is going to be that the force of tension has something to do with this constraint. The force of tension actually makes sure that this constraint is satisfied. That's what we want to talk about. But before we get into the Lagrangian way of doing this, or the Lagrangian formalism, let's go back and do it using the old Newtonian way, right? Let's try to see what we can learn about the system and using Newton's law. Okay. So if Newton was working this out, he would say there are two forces acting on this mass. So that is mg, and that is a force of tension, P. Right. So force of gravity and force of tension. That's the only two forces. Is there any other force acting on it? We are saying there is no air resistance or any of that stuff. So two forces. So Newton's law, Newton would say mass m, the system in this case, m times the acceleration of the mass has to be equal to the vector sum of all the forces acting on it. So there are two forces acting. So it is the vector sum of mg plus the force of tension P. Right. That's your Newton's second law. That's the equation that governs the simple pendulum in vector form. So in that sense, it is abstract. But for anything concrete, we have to take the components, right? This is in 2 dimensions, so we have to take the components of this equation. Let's usually x and y is good enough, but we would like to have this angle phi in it. So let's introduce the coordinates r, that's going radially down, and angle phi, this is phi hat, that's r hat. Is this visible on the board?
Yes. Yeah.
Yeah.
Okay, so that's the two quantities, but we have to now write all these quantities in the r and phi terms. So primarily, it is the acceleration that is slightly tricky part, but it's not that bad. Right, we have done this in undergraduate class, so let me go to the second board, right? So let me go and see what the acceleration is in this case, right? Let's do this quickly. The position r is equal to the magnitude r times r hat. If you're with respect to the origin, everything is the position of any point is simply in the direction of r itself, and velocity then is time derivative, right? Straightforward. But now you can take two derivatives, either the magnitude or the vector, and you would say this is r dot. The dot means derivative with time, okay? Times r hat plus r times vector r hat, right? The derivative of the unit vector. But we know that the derivative of the unit vector is actually omega, which is phi dot, and in the direction of phi hat. Is that, this is all old from your undergraduate physics, right? The rate at which the radial direction changes is given, is related to the phi hat. So this is equal to dot hat plus times phi dot and phi hat. That's clear. Velocity in the radial direction plus the tangential velocity, which you would say is omega times r time in the tangential direction, which is phi hat. Okay, any questions on this? We should have seen this before, I'm sure. Let's do the acceleration. That's what we are interested in. Acceleration of something going in a plane in terms of the radial coordinates r and phi hat. Now you do velocity, rate of change of velocity, and now there are 5 terms, right? R dot, r hat. There are 5 terms. Each one of them you take the derivative. So first one is r dot times r hat plus r dot, and keep taking the derivative. So let me write the rest of them in the second line. Of r dot phi dot hat plus r phi double dot hat plus phi dot phi hat dot. That's your 5 terms. Immediately you say that this r hat dot is already there. I should also say what is phi hat dot. That's the rate at which the tangential vector is changing. That is equal to negative phi dot and times vector r. So that's towards the center, right? The rate at which the tangential direction is changing is towards the center. It's like saying that the change in velocity leads to an acceleration, which is radially inward. That's the centripetal acceleration. So overall, this leads to, we have 2 terms giving you r hat, and I substitute this in here, and that's equal to r double dot minus r phi dot square. And these 2 terms are identical. So that's plus 2 times r dot phi dot minus No, there's pos, right? So pos r times phi w. So this is the usual radial acceleration. This is the tangential acceleration. This is the centripetal acceleration, again in the radial direction, but inward. So this is the centripetal acceleration. And there is this fourth term. What is that correspond to? Have you seen this before? Any physical interpretation of that?
Angular acceleration.
Isn't it called Coriolis force or something?
Good. Coriolis. This is what contributes to the Coriolis force. That involves a change in position and change in angle, right? So both are in there. Contributes to Coriolis force. Let's call it Coriolis axle acceleration. Right? And where do you see Coriolis acceleration or Coriolis force? An example where Coriolis force is seen.
I don't know if this is correct, but like a car moving in a like a circular path or something, like the angle changes and the position change.
Centripetal, right?
Ah, okay, cool.
That would be centripetal. Remember, you need R dot for that. Like car moving in a circle would be, you can keep it constant, right? It is possible to keep it constant. Or at least I presumed that when you said car is moving, turning, it is keeping the radius the same. If the radius is changing, then you get a Coriolis contribution. So that R dot is important. So any other effect you can think of which involves Coriolis effect? Have you heard of Coriolis effect before, by the way?
Yeah, I'm trying to remember from my.
Does it happen during rotation or something?
Yes, it has to be. So notice angle has to change and the R has to change. Right, so you have to be going in a circle, and while going in a circle, you have to change your radius. So for example, you're standing on a merry-go-round.
Spiral motion, is it then?
Flat surface, and you try to walk out of the. So when you try to walk outside on the merry-go-round, then you will experience this force. But what was the example you were suggesting, Anshula?
When you said radius also has to change, is it a spiral motion then?
Yes. So so for example, you're going in a circle and you try to walk outside.
Yeah, okay.
Walk radially outward. So that's when you experience this force. And a classic example where you see this is a hurricane. Okay. So hurricane affect the way it moves, and there is a certain direction sense a hurricane has. Is that familiar? If you are in the northern hemisphere, the hurricane moves in a certain direction, and if you are in the clockwise or counterclockwise, and if you are in the southern hemisphere, it goes in a certain direction. That's a Coriolis force. So as it comes on the equator, so this wind is trying to change its radius. So as it moves towards the north, let us say its radius is decreasing. Is that clear? Because the equator is the largest radius, right? So as it moves up, as far as the distance from the axis is concerned, it is getting smaller. So its radius is changing. Is that clear? Roughly? No? So what I mean is tangent now. So if this is visible, this is so here. So if you are in a sphere, this is radius r. If you were to go up somewhere here, the radius has decreased, right? Is that visible, that diagram? So as the wind moves upward, north, the radius from the axis is decreased, and that's your r dot. So there is a Coriolis effect in there, and that makes it turn. So it won't stay as it is. So as it is moving upward, it will try to turn, and I think it will be counterclockwise in the northern direction, and it will be clockwise in the southern direction. But that's, I'm trying to just imagine it in my head. I might be wrong. But you will also hear certain things that if this were true, when you flush your toilet, correct? Your toilet should flush clockwise in the northern hemisphere and should flush counterclockwise in the southern hemisphere. Is that true?
Not true.
Not true. And why is that?
I don't know why it's not true. I just know that it's not.
Yeah, that's a good point. It is not true, but effectively, okay, theoretically speaking, yes, that's correct that it should do that. But this effect is really small. So 2 times r dot times pi dot on the surface of Earth is extremely small. If you calculate it, it's I think about 1/100th of the actual centripetal force you have. So it is not really going to contribute to the extent that you will actually start seeing your toilets move around. But it can be increased. So why do you see hurricanes going in that direction? Because hurricanes are really huge, right? So it depends on the radius of this circular motion that's going on. So for hurricanes, yes, that is correct. But for toilets, it's not true. And you will see certain videos where they actually fudge this. Have you seen this? Where if you're going in a place where, in a country where you're on the equator, they will put a small funnel, pour water in it. They will go 10 steps on the southern side of the equator, pour some water and show you that, oh, this is clockwise. Walk on the other side, cross the equator. Oh, see, now we're on the northern hemisphere, that goes in the other way. But that is actually faking the whole thing. But anyway, so that's your acceleration, right? That's the 4 possible accelerations in a plane. And now let's come back and let's see how Newton's equation look like in this case. So mass times, oh, before that actually, I can do one more step here, right? So let me keep doing this. For our scenario, R is fixed, right? R is equal to L. That's fixed, which means that the magnitude of the position is fixed, which means that R dot is equal to 0. Right? That's what we have for the simple pendulum. So all these equations get significantly simpler. No Coriolis effect in the pendulum. So acceleration is equal to R double dot is 0. So
if the pendulum was like really, really big with the Coriolis, if it was really big with the Coriolis,
yeah, or in your lab, for example, you can have a Coriolis. So let's just make an elastic pendulum. So think of a pendulum which is stretchable, and if you were to swing it, you will get a Coriolis component in that. Surely you will get it. Yeah, I never tried to analyze that problem analytically, but it should be doable. Like especially if it is in a single plane, you will see this. Okay. And the main idea is that you're trying to go outward, but the force is perpendicular to you. So it's a non-trivial force in that sense. Anytime you have, it's like a magnetic force, right? A magnetic force is velocity is going, the magnetic field is in one direction, velocity is in another direction, and the force is in the third direction. So it's a sort of a non-trivial effect in that sense. You don't expect to go fall in that direction. So similarly, here you're trying to go outward. You would think that, oh, I will fall forward or backward, but counterintuitively, you will be pulled towards your left, right? So it's not a comfortable scenario. So very much like bicycle, right? Bicycle, I think in some form probably it is happening, but there it is the change in angular momentum. So that any gyroscopic effect, it's very non-trivial. Learning a bicycle is not trivial. Right? Eventually you learn it, that's perfectly fine. But in the beginning, you're falling this way and you do the opposite, right? Instead of turning this way, you do the other way. It's very non-trivial. So things like that. So we have our acceleration. So acceleration is minus L phi dot square times r hat, right? Only the first term doesn't contribute, Coriolis term doesn't contribute, and that is a tangential force, and that's plus L phi double dot. That's your tangential acceleration. That's the two contributions to the acceleration. This is a centripetal acceleration, and that's a tangential acceleration. At what rate is your phi changing? Since it's a pendulum, it's not a circular motion going with constant speed, so that's as a tangential acceleration also. Okay. So now let's go back and get into the old our Newton's equation. Okay. So that's equal to, so I can now put that acceleration in there. So it is mass times minus L by square by L by that. Acceleration is equal to mg is vertically downward, but I want to break that into r hat and phi hat, and that will be equal to, so in the r hat direction I will have cosine phi, right? So this mg r plus, first let me write the tension force. It's equal to mg cosine phi in the r hat direction. Then there is a minus mg sine phi in the phi hat direction. And that is a force of tension, which is in the radial direction, but in the inward radial direction. Oh, very familiar. It should be very familiar. Maybe doing it in a different notation, that's all. Twice the same old pendulum. So there are two information in here. The first one is the force in the radial direction, correct? So pick up all the radial pieces in there, and you get the radial force in here, and this is equal to minus m L phi square, right? That's a centripetal force, if you want, and that's equal to mg cosine phi minus t, right? The force of tension. And in the phi hat direction, we have ml phi double dot, and that's equal to minus mg phi. Of course, mass cancels out in the second equation. Second equation is where the motion is really happening, right? Phi is really changing and the mass is going, that's a variable. So that's dynamics. So this is the equation of motion, if you want. That's the equation of motion. Because the mass is really going along that direction, but along the r hat direction, the mass is not going. That's a constraint. this equation is only a constraint. Nothing is happening in that. So this is a constraint equation. So a force, all the forces that are contributing or are conspiring so that Newton's law is obeyed in that direction. That's what the force of tension is doing. That's constraint equation. That's constraint. So that's what I meant in the beginning when we said we're going to talk about constraint. And the whole philosophy of Lagrangian formalism is that somehow get rid of the constraint equation. You don't want that. Things are not happening in that direction. That's useless information. Get rid of that and get only this. So that's how you proceed. But here now we're going to see, so what Lagrangian multipliers is going to do is reintroduce the constraint somehow, and can we get the information of T somehow? Okay, that's what we're going to do. So let's now go back and do the same problem using Lagrangian, the usual Lagrangian, which you have done 5 times, I think, in this class. And then we'll come back and do the Lagrange multipliers. Okay, any questions at this stage? Okay. So we have, this is our equation of motion. That's the constraint equation is x squared plus y squared is equal to L squared. But this is the forces that have to be set up so that motion does not really happen in that direction, right? In that sense, you will interpret this as a pseudo force stuff because things are not really moving in that direction, and that's the philosophy.
How did you decide the first one was the constraint and second was the equation of motion? From how did you infer that?
Things are not moving in the r hat direction, right? There is no motion actually in the r hat direction because of the particle is going in a circle, right? It's not changing its radius, right? So, so in that sense, there is no motion there. So if it's not a motion, that means it's a constant, right? If you have a coordinate, or let's say that it's 4th dimension in our universe, which we can never reach, so we are constrained to be in the 3 dimensions, right? It might be there, but then we're saying that.
R hat will be changing, right? The magnitude R will not change, but every time it moves, the R hat will be.
That's correct. R hat will change, but R doesn't change. So in that sense, yeah, what I mean is that there is no motion along, or R is not changing. Magnitude of R is not changing. That's the motion. That's correct. That's correct. That is what this force is actually. Right? This is coming because of the change in direction. You're correct. So R hat can change, yes. So if you want, the constraint is that the radius has to be fixed. Now, there are various things that come together to make sure that the constraint is satisfied. So, for example, there is a force of tension, which will be the primary player here. And these two are already taken care of in the sense this is gravity. We know that that's going to be there. And this is a centripetal force, which is what you're saying because of the change in direction. But the force of tension has to compensate that so that Newton's law is satisfied in it. Otherwise, there will be actually motion in the radial direction. It is not for the force of tension. So that's going to be the key. But more than, so that's our interpretation here, but we're going to see what should we do to see this force of tension in the Lagrange. That's what Lagrange multiplies. Did I sort of answer your question? Right, sort of helped?
Yeah, it did.
Okay, so let me erase this part. I think we don't need this acceleration part so that I have some full space. So let's do this problem using Lagrangian. Right? So you have Lagrangian would be is written in terms of x, y, and then we have x dot and y dot, right? If we were writing in terms of x and y, but very quickly I will get it in terms of y. So that's equal to, you have Lagrangian is kinetic energy half mv squared, and the minus potential energy, which is minus mg in the y direction, right? So that's minus mgy. But remember, y is measured with respect to the top, that is negative. So that actually will change sign. So that's equal to, you see that half mx dot square plus y dot square. Again, we've done this, but this is y is so x square plus y square is equal to L square, right? So x square plus y square is equal to L square. And since in the diagram we have this angle phi, we do know that in polar coordinates x is equal to L. X is L sine phi, right, in the diagram that we have. And y is equal to minus L cosine phi. That's your variables. So mgy will be mg times L cosine phi. Correct. That's what your Lagrangian is. This is the equation of constraint, x squared plus y squared is equal to L squared. But let's see how this looks like. Let's take a differential here. So it is 2 times x dx plus 2 times y dy. That's equal to change in the length, that's 0. At this stage, I can even divide it by dt, a small change in time, and then I can learn that, oh, x times x dot is equal to y times y dot. So that's another way of writing the same constraint. Right?
Minus.
Thank you. Right, that's minus y y dot.
Y
In
is
Lagrangian, the second term should be positive, right?
yeah, you said y is equal to minus L cosine.
Oh yes. When I substitute this in there, I intended to do that. But
Yeah.
okay. And once you have that, you can either start from here and get the x dot square plus y dot square, but it's much easier to see it here itself. X dot is equal to L cosine phi times phi dot, and y dot, the change in y velocity, is actually, there's already a negative sign, but derivative of cosine gives you another sign, so that's L sine of phi times phi dot. And together, when I square these quantities, it's clear that x dot square plus y dot square is actually L square times phi dot square. Again, that's in this, we've done innumerable number of problems that this polar coordinates shows up, and that's what it is. So the Lagrangian suddenly does not have any, instead of 2 variables, there's only 1 variable, so that's phi and phi dot. Like, 1 variable in the sense only 1 dynamical variable phi, and it's a change in phi that is involved. So x and y are not necessary, and that's because one of the variables got lost in the constraint, right? So now notice you're getting rid of the constraint. That's the whole idea of the Lagrangian, that don't worry about the second equation at all. And that's equal to half m L square y dot square and plus MGL sine phi. That's your Lagrange. So really, it's already 10:30. So once we have the Lagrangian, we find the generalized momentum, right? So that's phi dot, right? Canonical momentum, and that's got by taking the derivative with respect to phi dot, and that's in this case it will be the angular momentum, L square, the canonical momentum or the generalized momentum, and that's your phi dot. And time derivative of the generalized momentum is m L square phi double, correct? That's your change, rate of change of angular momentum, which is the torque, which is supposed to be equal to torque, and the generalized force, which is torque in this case, that's equal to minus mgl sine phi. You relate the two quantities together, and you get the same equation. Right? So it's m phi dot minus L.
Can you move the camera down?
Camera down. Sorry, yes. Okay, sorry about that. We can move it in the right time. Yeah. Clear. So again, if you missed what I was writing, there's a Lagrangian. I calculate the generalized momentum, which is the angular momentum in this case, to the generalized force, which is mgl sine phi. Put it together in the Euler-Lagrange equation, and you get ml square phi double dot is mgl sine phi, which is exactly the same equation you would have got for the tangential force equation earlier, whatever we did. So that does match, correct? But what about what if one was interested in the radius or the tension force, right? One might be curious about how could you capture the force of tension in the Lagrangian formalism, and especially because often we have situations where there are constraints, for example, as simple as being in a plane, or we are confined in the three-dimensional space, and you would like to write a theory where you are confined, but something else is not confined. Like that's the current, like if you heard of string theory, the theme of string theory is that gravity can propagate outside 3 dimensions, but we cannot propagate outside 3 dimensions. Like V means electromagnetism and other forces cannot propagate into the 4th and many other dimensions that's there. So when you want to construct such theories, you want to involve this constraint, and how can you build it at a Lagrangian level? So that's any questions at this stage? And now I'm going to introduce the Lagrange multipliers. Right, all this is review, very making it very crystal clear what things mean in each of these formulas. Any questions at this stage? Okay, so let's go to the other side of the board, and now let's go back and let's write the same Lagrangian, but this time let me write it in vector form. So just for nothing special. So the same Lagrangian, this time instead of x and y, I write the vector r, and instead of x dot y dot, I write velocity v. So it gives you the insight better in vectors when we do this. Okay, so that's equal to same Lagrangian, so it's half mv square, and minus, right, minus mgy. Okay, so let me quickly, this is g is downward and radial direction is r hat here. And when I say mgy, it's equal to minus mgl cosine phi. But whenever you see cosine phi, that's the same as a dot product. So this is the same as minus mg as a vector g dotted with the vector r. Right, that's the same thing. So remember, f dot dl is your work done, right? That's how you get your potential energy. So that's where that shows up. Substitute this in there, so this changes sign. So that's plus m g dotted with r. So same information. Here we work with explicit coordinates. That's in vector form. Okay. So that's your Lagrangian and vector dot product form. Should not be anything new at all in here. Okay. And that's okay, good, great. But now also I will say that this is x squared. I have a constraint x squared plus y squared is equal to L squared. I want to write this also as a vector equation. X squared plus y squared is nothing but vector r dotted with vector r. That's equal to L squared. Which is the same as saying vector r dotted with vector r minus L squared is equal to 0. So constraint is saying the dot product of the position with respect to that origin, which is at the hinge, is L squared, right? It's fixed, so that's great. The Lagrangian is kinetic energy minus the potential energy, and the Lagrange multiplier is all about adding this constraint equation at the level of the Lagrangian itself and say this is r dotted with r minus L squared. That's 0 anyway, who cares? Right? Lagrangian is not going to change. Like it's exactly 0, right? That's a constraint. Okay. What's wrong in what I wrote? Like very simplistically, very trivially speaking, nothing concept. But immediately you should have a botheration that a very first chapter, first principle, there's an error in that, in this equation.
If it is 0, but dimensionally doesn't make sense. Right?
Perfect, perfect. This is not dimensionally correct, right? This cannot be dimensionally correct. There is length square here, and these are energies, right, in joules, and that is length square. That's not okay. So we put a constant in front to fix the dimension, right? And that's what is called a Lagrange multiplier. Lagrange multiplier. Pretty much to take care of the dimension, but it has more depth in here and is arbitrary. It's arbitrary. We don't know what that is except for its dimension. We absolutely don't know what that is, but we will see what that means. Can I erase this here? So that's how you proceed. Write down your Lagrangian as you would do in the usual case, and the constraint is added on to the Lagrangian, and now you argue that that's a 0, so that shouldn't change anything. And now let's work out the same old let's use Lagrange, Euler-Lagrange equation. But this time, this is here in the earlier case, we used the constraint. But now we are not used the constraint, so there are two variables nowadays. And in principle, that's x and y, but now we will do it in the vector form. So we again do your canonical momentum. That's with respect to velocity, right? That's your generalized momentum or canonical momentum. And that's equal to take the derivative with velocity. That's the same old mass times velocity. Nothing changes because your constraint did not have any velocity in it. Constraint equation did not have any velocity in it, so that remains the same. That's your generalized momentum. Now, the generalized force. Earlier, you would have got a contribution from the gravitational potential energy. That's mg. But now, this is 0, true, but that has a position, it does contribute, right? It does contribute in the generalized force, and that is equal to plus lambda times vector r. Is that correct? No, right? 2 times lambda r, right? Like r squared 2 times r, so it's 2 times. I think in the recording that I made an error there. So that's a factor of 2 in there. Okay, any question on that? And L squared does not contribute because there is no R in that. That's just a constant. Any questions at this stage? Your Euler-Lagrange equation, next step is to write the Euler-Lagrange equation, which takes the time derivative of the canonical momentum and sets it equal to the generalized force. Time, rate of change of velocity is acceleration, so you get your equation of motion as mass times acceleration is equal to mg plus 2 times lambda times vector r. Okay. So let me, since vector r hat is actually, let me just write. Okay. That's what you learn from here. But then you compare it with your first equation that you wrote down all the way back, Newton's law, right? For this pendulum is mass times acceleration is equal to mg plus force of tension. And you immediately see that this Lagrange multiplier is nothing but the force of tension up to a scale. So let's see what that is. So they compare the two. It says that 2 times lambda times vector r. Vector r is nothing but L times r hat. And the force of tension was minus T times vector r hat in the direction. So it's clear that lambda is equal to minus T over 2 times L. Can you guys still read it? Oh, yeah. So I was trying to do it up. Okay. So Lagrange multiplier, the way this, even though we just innocently added a 0 term in there, but the coefficient captures the force of tension and up to a scale. So the Lagrange lambda is tension up to a scale. Remember, it was arbitrary to begin with. I could have put that 2L in there, right? And it would have been exactly equal to the force of tension. So it's all about setting the right coefficient in front. Why does it do this? Because as I said, whenever you talk about a constraint on a surface, there is a force that has to keep things in there, and the gradient, right here, derivative with r is a gradient of a surface, equation of surface. Usually there's an equation. I think of the gradient of x squared plus y squared is equal to L squared. What is this equal to? What is this equal to? Gradient of an equation of a surface. What does it give?
Negative lambda times gradient of constraint.
Negative what?
Negative lambda times gradient of constraint.
Yeah, but what is that gradient of constraint? Yes, good. What I mean is, suppose equation of a surface, right? Let's say it's a sphere. This was a sphere. So the surface of a sphere is defined by x squared plus y squared plus z squared minus half squared. What will you get even without, before you evaluate? Like you can of course go ahead and evaluate that, but just intuitively, what will you get?
Plane.
Huh?
Plane is an equation of a.
This is equation of a sphere. Think of any surface, but sphere is the easiest.
I would get line.
Yes, Avinash?
I would get line.
You get a line. No, that's not correct.
Equation of a plane, right?
No, this is not an equation of a plane. This is the equation of a sphere.
Gradient would be. What was your question?
Of equation of a sphere will give you what?
Gradient of equation of sphere.
Yes.
View what? It's not a plane?
Not a plane. Think of gradient. What does gradient mean? Gradient of something is what?
Normal to the
Normal, right?
surface, yeah.
So this will be r hat. If you were to actually do this, this will be exactly r hat. Let's say some constant if you want. Okay, that might be factor of 2 or
Okay.
vector r, because the dimensionally it has to be true. So this will be vector r, right? So gradient of anything will always be perpendicular to that surface. So that is a surface we are talking about. Gradient will always be perpendicular to that. And here, there is an equation of a surface, or we are talking about a constraint. That constraint can be imagined to be a surface. Whenever we have a constraint, we have an equation. That equation is an equation in terms of few variables. That's an equation of a surface. And this gradient, when you take the gradient with respect to the Lagrangian, actually is giving you the gradient of that surface, and that's the normal force, or that's the force of tension. That's why the force of tension is always perpendicular to the circle, right? Normal force is perpendicular to the surface, so that's by construction, or that has to be true, because that's what makes it stay on the surface. So what is a Lagrange multiplier? That's actually pretty much captures the force that keeps the system in a particular constraint. Okay, and this is one of the simplest way you can write a constraint. It need not come up in this manner. Let's now. I have. So next time we will talk about other kind of constraint. For example, a wheel rolling on the surface of a road, correct? We usually say perfect rolling, correct? That leads us to the first example that we discussed on the first day of class. as to when a wheel is rolling on an incline, what is the direction of the force, right? We will address that next time. And there we will be talking about perfect rolling, and that's a constraint. It doesn't slip, doesn't slide. A constraint, and how will we encode that into this as an equation? We will see that. By the way, yeah, I should tell you, if you give me a few more minutes, in your exam there will be only one important question, and this is what it's going to be. You can start thinking now itself. So this is related to this topic. This is an example.
Everything else except for this.
Say that again.
So this is the only important part you're saying?
I said in the exam I will grade you mostly from that part. Rest of it I'll make it simple. It will be more mechanical that you will actually keep working on. So I'm very glad, because I was very much, this is what I did in my 2 weeks. If you want, it occupied me for quite some time. I had to struggle a little, but relatively, once you figure it out, I think it's easy. So you have a gear kind of system. So this is 2 discs, if you want. One is radius R1, and the other is radius R2. Let me not write, because it will take away the space. And typically you think of it as a gear, right? If you roll one, the other one also rolls. But let us say this has friction in between them. Like there is sufficient friction that when you roll one, the other one also rolls. So let's say this is rolling in this direction, or this is the direction of motion of the first disc. So it's 1, and the other one is 2. And immediately the first question you ask is, what's the sense of direction of rolling of the second one, correct? And that could be that should be immediate. But now let's say that the center of this disc is free to move. If let go, it is free to move, but only free to move on that circular path. Okay, it cannot move away. So that is a constraint there, right? And the question is going to be, in your exam, is going to be, if you move it this way, will the center of this small disc move clockwise or counterclockwise, or it might even just stay there, right? So out of the 3, what will it do? Intuitively, you guys can think about it. And does intuition tell you anything?
Intuitively, I just said it would move clockwise because of gravity, right?
It'll stay.
Oh, there is no gravity by this. This is flat. This is flat. Okay, get rid of that. Think of it as on a flat surface, so that we don't have. I mean, you can keep gravity, but let's not have it. Okay. So then the question is, yeah, think about it.
Well, it'll stay.
Huh?
I think it'll stay.
It'll stay. Oh, it'll just stay here. You're saying, so just stay, not move at all. Okay. Yeah. So we'll think about that, and we'll come back and do a little bit of.
I think the second one will just roll and not move.
Second one will what? Float.
Second one will just rotate on top of the first disc and not move. Just rotate.
That's what Jordan was also saying, right? Jordan, you also said that it won't move.
It won't move around in a circle, though. It'll stay in its current position. It'll, because the contribution of the same as like rolling down the hill. The different parts have different. How do I explain that? I think it won't move.
Yeah, that's what we will discuss next time. So until then, think about it, look it up, Oh, that's extra credit, let's say. Can do extra credit, right? Yeah, what direction does it move? Think about it. And in the exam, you will do it more formally. So let me know in what direction will it move? Yeah, clockwise or counterclockwise.
Does this problem have any name? As in, is it something we can Google up and read more
I don't know. I mean, I didn't search too much. Gears, maybe? Like, no, I think, no, hold on. Look up, because this started because someone was asking me, how does a cone roll on another cone? That's how it began. And then I started thinking about that, and I thought that was unnecessary. Even this has nice features. So look up cone rolling on another cone. And there is a formula for that in Wikipedia, but I think we don't have to worry about a cone. Cone is hard to imagine. Even a simple disk has nice features associated with it. Okay. Or perfect rolling of a disk on another disk. Look it up. Perfect rolling without sliding or slipping. Okay. Yeah, that's all. So yeah, we had an extra credit also in this online form. Let's look at this.
Is it right to say it doesn't really matter what size the gears are?
Oh yes, R1 is, as I showed, R1 is larger than R2. So that's another point. Yes, as I showed in the diagram is to scale. Let's say. And just something to think about.
Because shouldn't their velocities be the same?
Problem. Huh? Yes, Jordan.
Shouldn't their velocities be the same at the point of contact?
Yes, because that's the constraint, right? Yeah, velocity has to be the same at the contact. Yes, that's correct. That will be the constraint. Yeah. That you're going into detail. That's correct. That's correct. That's a correct statement. I can tell you that that's correct. So that's a hint if you want. Yeah. Yeah. Good. Yeah. Think about it. So it bothered me for some time.
Okay.
By the way, what is the direction of the friction on your wheels of the car?
Backwards, the opposite direction of motion.
I think it's in the direction of motion.
Does it again?
I think it is in the direction of the motion. Right?
Your wheel spins on the bottom. It's putting force in the opposite direction, so then the force would be in the same direction as the car, right? The wheel spins. When it hits the bottom, if it's spinning this way, the direction of friction should be opposite. It's causing you to be pushed, so it's got to be in the direction of the car, right?
Yeah.
Going that way? No?
Oh, I don't want to reveal the answer. Anyone else? Moses?
What Jordan said sounds correct.
Because if it was in the opposite direction, then your car would want to go the opposite direction.
Exactly. Right. If Avinash was correct that friction is in the forward direction, then as the car moves, that friction should be helping motion, so it should accelerate, right?
Mm-hmm. Yes. Is that right?
But then I can argue the other way also. If it is in the
Oh, I see. It's perfect rolling there, and then it does not matter. The friction becomes zero.
There's no slipping or no.
But I was saying that if it is in the backward direction, the torque due to that friction,
the friction between forward and backward is equal. So the effective friction is zero. I don't know.
Okay, say what you were saying again.
I was
So what-
saying if the friction was backward, that friction force exerts a torque, correct?
Yes.
Which helps you move,
Yes.
which means to say that it should help in motion, so it should accelerate the wheel. So yes, it will reduce it will help you slow down linearly, but it will accelerate in the circular direction. So as you're moving, you should go faster and faster. It's like it's helping you move. So that also doesn't seem very correct. Okay, that's the second extracted problem. What's the direction? And remember also that there are 4 wheels in a car, right? Is it the same for all 4?
I mean, to say that the friction wouldn't contribute doesn't make sense to me. Because it does contribute. It has to.
Yeah.
If there's like if you want to say like effectual contribution, maybe it doesn't. But
Yeah.
if you made it ice, you're not going to move anywhere. So friction is necessary.
Of course. Yeah, friction is necessary. I agree completely. So let's make this question a little more precise. What's the direction of friction on the front wheels of the car? And what's the direction of friction in the back wheel of a car? And by that, when I say I'm assuming that the car is a front wheel drive, does that mean, do you guys all understand what that means? Is that the machine, the actual car, the machine is connected to the front wheels. Okay, so that is a mechanical motor that is trying to rotate the front wheels. The back wheels are just rolling with it.
Yeah, they're different. They're different. They're not the same.
Yeah, so they will be different in front and back. So
Giving some
tell
torque
me the correct answer.
Giving torque to the front. There's torque. You're giving, you're applying an external force to the front wheels. And the back wheels are just following.
Yes.
If you lifted the back wheels, the car would continue to move in the same direction of motion. As long as you didn't lift them too high,
Okay, make it more precise and let me know. Okay. And be careful reading the internet. This is everywhere on the internet, but I think it is discussed in all kinds of forms. So be careful when you're reading. Use authoritative sources.
So you should give us the right answer at some point.
Yeah, I will. Next class we will settle this. Okay. The incline and yeah. The key is that friction always opposes the tendency of motion. That's the key. In the front wheel, the tendency is to rotate. In the back wheel, the tendency is to pull. The tendency is to go forward, right? Not to rotate. Back wheels are
it would still be rotating, right? If
It
it's
will be rotating, but no one is making it rotate. It will rotate, yes, but the tendency, someone is pulling it forward. Who is pulling it forward? The front wheels are pulling it forward. So the system has to resist that. Otherwise, there will be perpetual motion. Right? So system has to oppose that. Similarly, in the front wheels, the machine, the motor is trying to rotate it. So the system has to oppose it.
Let's take away the spinning of the back wheels. Let's put wheels there, but let's limit its motion so that it can't spin. If the back wheels can't spin, the car will either slow down until you give it more gas, make the wheels spin faster, or let's say you're going and the wheels are spinning and then you put only your back brakes on to stop the spinning motion. Well, then the frictional force from the back wheels will oppose pulling of the front wheels. So they should be opposite. But now let's let them spin. That's still there, but you're limiting the force of friction in the back, is it still going to be the same as the friction of the front though? That's where I don't understand.
I think I completely did not follow. Let's have this discussion next time. I think it will be more complete. It will be more complete because, first of all, this is your homework also, by the way. In this homework, this is your problem.
Okay.
Front or back. Or I will just talk about a single wheel, but one can extend it to as many wheels as possible.
Wait, how would it be the same as in a single wheel? That would be different.
The idea is the same, I meant. The basic idea is captured in a single wheel, and then you extend it to whichever wheel you want. If you want to refer to my notes on this, I think I have, there are notes on Physics 205, which is available on internet. If you go to my website, I think there is no explicit link. If you search for my name and what is it called? Calculus-based mechanics. I think it's called calculus-based mechanics or calculus-based physics. And I have lecture notes on that.
Or is it on your page on SIU?
On SIU, yes, but it's just there is no explicit link for it, so I cannot give you where to go. But if you search on Google, you will see it. And somewhere in the on the chapter on friction, I have a one-page discussion on this, the front and back. So look it up. Okay. Like since you guys keep telling me that, oh, I can.
So, one more thing really quick, just because it's bothering me. Say you have like, thinking of like a train, okay, a train moving on the tracks. There are parts of the car or the cart that are moving backwards with respect to the direction of the train itself. Like the bottom of the wheel or the disc is moving the opposite direction of the car itself, right?
Not car itself, it will be zero at the most. It won't go in the opposite sense. Can it go in the opposite sense? No, right? Yeah, it will be zero at the most, I suppose. I think it will be
as a whole sum, yes, but from one position to another.
Yeah, it is going backward. Yes, I see. Yeah. Yeah.
Which means at that backwards place in motion, in order to go, the friction opposing the backwards form of motion is causing the vehicle to go forward.
Yeah.
Okay.
Yeah, that's correct.
It's the right thinking.
Yeah.
Okay. All right, I'll look it up.
And if it was perfectly rolling, it is at rest at that point. So the 2 points which are in touch, the wheel touching is at rest with respect to each other. But that doesn't mean that there is no friction. Simply because something is at rest, there is no friction. Because if you push me, like now there is no force of friction acting on me. But if someone comes and pushes me to the right, force of friction is opposing that motion. Is that clear what I mean?
Mm-hmm.
Right. So simply because you are at rest doesn't mean that force of friction is zero. Let's discuss this next time, or unless you want to keep discussing.
Okay.
You guys don't have any other classes?
I
Avinash?
think I don't. I have one class at 4:30.
Okay, so you want me to discuss this for another 10 minutes then? I can
Yeah,
give you.
I was gonna say in the front wheel, the friction is towards the back side. And in the rear wheel, the friction is towards the front side. So the overall friction in the car, if we look at 4 of the wheels, it becomes 0, right?
No, first of all, whatever you said is exactly the opposite.
Okay.
It's exactly the opposite, and they need not cancel. They could be different. They are independent.
If they cancel, the car doesn't move, or the car bounces.
No, the car rolls.
What you were saying something about perpetual motion though, which made us think that the directions have to be, of the front and back have to be opposite each other.
Yeah.
No, for example, okay, let's do this. Okay. Like you can have force of friction and still have no motion. That's one feature of force of friction, correct? So let's see. Okay, so let's say let's have two wheels. I think this is the discussion I have in that. So, and instead of talking, this is four wheels or two wheels if you want. So this is connected. Oh, that's the surface. And there is a motor connected here, so that means this is forced to move. So that by this I mean there is a torque. So there's a motor attached to that that's forced to move in that direction. There is no motor connected on this. Clear? Yeah. So, so the way at least I try to imagine this is, or I try to remember this is, first of all, the force of friction could be in the forward or backward direction. Let me say that this is in the forward direction. Pretend, or let's pretend that it's in the backward direction, right? That's what Avinash said. So that's a force of
Now the hair moves backwards, though.
Yeah.
That's,
This is
that's like it's a ball rolling down a slope.
That's different, or that's so very similar. Again, all the rolling wheels have similar arguments. Okay? But this is two wheels connected, so in a sense, slightly different. There is a vertical force of mg acting. There is a vertical force of n acting. There is no other force acting on this. Can we agree on that?
Mm-hmm.
Right. Oh, there is also the, like, this is going to resist, right? Suppose we are talking about this is wheel 1 and that's wheel 2. 1 will pull 2 and 2 will pull 1. Correct? So that will be another force here, the force of tension. Agree? That's a only two forces acting on it. Clear?
Mm-hmm.
But now let's talk about rotations. Rotation of 1, and for that I have to actually draw all the forces. So there is mg acting on the center, and the normal force acts at this point. So there are four forces. Is that diagram clear? Mg acts at the center of this. Normal force acts at the point of contact. And then there is force of tension, which acts on the axle, because we are assuming that this is a simple cart where the axle is getting pulled. So that's a force of tension. And there is a force of static friction, which I'm saying I did it wrong. Okay. But if that was the case, so let's say, what is the torque due to the gravitational force on this wheel? About the center?
0?
Huh? Zero, yes. Zero, correct? Because it's on the axle. You cannot open a door by pushing on the axis of the door, right? So that's 0. What's the torque due to the normal force?
Also 0?
0, because it's going through the axis. You cannot open a door by pushing on a door like at the along the direction of the door, right? So that's equal to 0. What's the torque due to the force of tension, which is pulling you back? We're saying that that is pulling on the axle, right? Like it is right connected on the axle. What's the force or torque due to that?
P times radius?
Yeah, but the torque is, I'm saying it is connected to the axle.
It's also 0.
it's also 0, right? If I design it like that, you can always design it in other ways, but then that's just complicating the problem, right? Let's have the scenario where this is 0, right? Everything is 0. So the torque, which is change in angular momentum, right? So moment of inertia of this wheel times the angular acceleration, theta double dot, right, has to be equal to the sum of all the torques, right? So there is only one torque remaining, and that's the torque due to friction. That's the torque due to the static friction. Okay. The torque due to static friction is going to make it rotate more, right? There is a force, so there will be an angular acceleration. So this will keep rolling just because of friction. You don't even need a motor, right? I haven't even introduced the motor here. Just because of static friction, this will accelerate. Is that clear what I mean?
If it's on a flat surface?
If the force of friction was in this direction,
Oh, yeah, I agree.
the torque due to the friction will help it roll or rotate, right? Because Newton's law tells us that if there is a force, it has to accelerate. So it will rotationally accelerate. So it will keep going faster and faster, even without the motor and switching off the motor. That's not acceptable. That's what I meant by perpetual motion. You'll start generating energy, right? So this must be in the opposite direction, right? That's not acceptable. So this must be in the opposite direction, right? That's force of friction, right? So this will be negative, and there is a plus torque due to motor. Right? That will be your equation of motion for rotational motion for this. But then there is a problem again, right? Now immediately you will say, okay, that's rotations. What about if I were to, what do you say, linear motion? Right. So let's analyze the linear motion. Can you read this? Oh,
Yeah.
No. Let me do the linear motion on the. This is the same for one. Okay, linear one. Like for the wheel one. Normal force doesn't help in linear motion in the x direction. Forget that. Gravity doesn't. So they are all vertical. So force of friction minus T has to be equal to mass times acceleration. If not for this T, the force of friction would help it accelerate. Okay? So which means that it will keep going forward, and that's what I was saying, perpetual motion in the linear sense. Right? So this will work, but the force of tension is going to help you. Right? So that's going to resist. So this is okay. This is at least doesn't violate any principle here. That it's not going to, even without any machine attached, it's not going to keep moving. And there is no nothing actually making you move forward. Motor is only going to rotate it, but this is what is going to forward. If the force of friction was 0, there is no way you can switch the rotational motion into linear motion. So if not for friction, you cannot do the switch. Do the same analysis for the back. Now, does that help you how to go further backward? It will be the same idea. Now the tension is in the forward direction. No torque. Right? Torque due to motor is not that. And you try to do the same analysis. And yeah, look it up on, I think I have notes on that. No, I think I have notes on that. It's called calculus-based mechanics. Just search it on Google right away, you should get it. Are you guys all using a computer or is someone using a phone? All computers?
Using a computer.
Computer.
So did I help sufficiently there?
Yeah. Yeah. That's what I was thinking, the way that you did it. That's what
Then we will talk about perfect rolling and then come to a point where it is really zero. And those kind of next time we'll make it a little more concrete. But the ideas are, I told you the ideas. Then we will do the gear. That's the exam problem.
Okay. All right.
Good. Okay. Enjoy. Do you have to work, Jordan, today?
Yep. I'm getting ready to go back to work. Just 2 breaks today between my 2.
So you still have to go out, that means?
Yeah.
To stay at home doesn't work for you. Huh?
No. If I stay at home, I don't know what I would do. I wouldn't be able to afford anything. I wouldn't even be able to afford my ramen noodles or my candy. I need to afford my candy.
But I didn't see you eating. You just kept it there.
Oh, let me show you.
Oh, really? You have eaten?
See the file? Candy wrap?
I don't think that's healthy.
No, it's not healthy.
But then you probably spend the calories sufficiently you work. Huh?
Sometimes I try a little bit. I'm not the healthiest person, unfortunately.
Even if you work out, that much sugar is not good for you.
Yeah, it's not good for you, but it's good for my taste buds. I love it. You know, for every
Still
action,
taste.
there's an equal and opposite, right?
So you have a circle, Moses. You have a circle, or what will you call it?
It's
It's a mandala.
yeah, it's a tapestry and it's got a mandala in it.
What is it in it?
Oh, well, a mandala. Avinash would be better at describing what that is.
Oh, yeah. Mandala is a Buddhist way of depicting the universe in a circle.
This is a much nicer.
Oh, yeah. That is much nicer. That's like heaven.
I got this in Nepal, actually.
Oh, you did?
Yeah.
Cool.
Yeah.
Cool. Okay. Good.
You have something else to show?
No, that's it.
That's it
For now.
for now. Yeah.
The weather bad there right now? Is it really rainy and nasty?
It's not
Well, it's
raining.
pretty
but
dark outside.
It is rainy.
Is it raining?
I believe so.
It is pretty dark outside. I can see that, but I don't know if it's raining.
Yeah, it is raining lightly.
Okay.
Want to see the creek outside my house?
Wait, wait.
Sure.
Can you see it?
Oh, it's flooded.
Oh, wow.
So that is flooding, or it's always like that?
No, there's a little creek that goes underneath the house.
It's flooded.
See?
You don't mean underneath the house, right? You mean adjacent to the house.
No. I'll show you.
You mean
It goes-
underneath
It
your
goes
house.
underneath the house.
That's
Yeah.
cool. Who designed the house?
It may get a little rainy. We're outside right now. You see? Can you
Yeah.
see?
Yeah. Huh.
That's very cool.
It's pretty cool. I'll show you.
So you designed it?
Yeah, see?
Oh, wow.
Yeah.
Huh. I thought you were joking. Huh. Uh-oh, internet.
Yeah.
That's
It goes
the internet is getting
Your
you.
internet is rubbing.
under the house. Yeah. My laptop's getting soaking wet.
Fancy.
So yeah.
Nice. That's a nice house.
I like a house like that. I want to build a house like that.
Yeah.
You
Honestly,
don't want a house like this because you have to work a lot.
house over a river.
If you want to go to school, having a house like this isn't good because you're poor all the time.
Maintain it.
You have to work a lot. Okay.
Nice. Okay.
Well, on that note, I do have to go to work, so
Yeah. Enjoy, guys.
I'll see you guys, some of you later today, probably.
Yeah.
Later today. Oh, maybe some of you guys are just.
We have like a question and answers
Yeah.
for quantum.
Oh,
Oh, I scanned the hydrogen atom notes. I'm gonna send those out to you guys.
Okay.
And if anyone wants to have a study session, I would love that because I really need to study for this exam.
I don't know what I'm gonna do whenever it gets here. I'm just gonna hope.
Hope for the best.
Hey, just cross the river.
Yeah. I'll just go drown myself out there in water
Hey,
and make me feel less, you know.
maybe,
I'm incredibly worried about this exam, especially because we actually missed a week of stuff for it. We were supposed to, the first week back, we were supposed to do another week of class. So here we go.
Yep.
All right. Thank you, Sajish.
Yeah.
yeah,
Thank
it's
you.
still recording, so all these discussions can go. I'm not going to edit or anything. Yeah?
All right. Cool.
So all this junk discussion. First, I'll put it private, and maybe we'll see how inconvenient it is. I'll need your
Just
email.
email us the link to your YouTube page, or
It is on the web page of the
okay.
course. Already you should see it, but it's just that if I have to give access to you or to a private video, I need your Gmail addresses.
Okay.
is that the same? Is that the same with the E&M also?
So you just want me to send you my Gmail to your email?
Yeah, then we can keep this private.
Okay. Whatever you want. It doesn't matter. You can make it public or private. I'll just send you my Gmail. Whatever you do, I'll follow it up. Fine with me.
Yeah. Since you guys all approved this, I don't really mind putting it outside, except that these discussions, if you guys don't mind, we have all. But that's okay. This is we didn't talk anything junk or.
I mean, it's nothing. It's nothing like we want to keep it private.
Nothing what, Avinash?
It's nothing like we want to keep it private unless Jordan wants to keep his home private.
No.
Do you want to stay under the radar or something? Then you should not.
In most walks of life, I'm very alone, but I'm okay with my Gmail being out there.
No, I was talking about your house. People in the internet seeing your house.
Oh yeah, whatever.
Outside, let's see how much that is a problem. I don't think there is any problem.
No problem. What are they gonna do? Come fish?
This is how the
People
class-
put random shit in YouTube. This is nothing.
Yeah.
Exactly. Okay, cool. Thank you. Yeah.
Well, thank
And
you.
then good luck with your exams on Thursday. Yeah. So Thursday you will be all disoriented, that means, in the class, huh?
Yeah, Thursday is gonna be a bad day.
Oh, we have 2 classes. Hmm.
Okay.
Okay.
Okay. Enjoy.
Bye.
All right.
Take care. Goodbye.
Have a good
Bye.
day.
Bye.
Mhm.